let's get back to work. We have seen ordinary differential equation with the regular point. That means all the coefficients are analytic at a given point. So we have seen that we can express the solution in terms of power series. Today we'll go ahead and further look at what happens if there are singular points and under what condition we can have a solution similar to the power series. Today we are looking at the properties of differential equation at a point regular singular point. This is a part of course PH3103 at IISER Kolkata. For an ordinary differential equation of the form d square y by dx square plus p of x into dy by dx plus q of x into f of y is equal to 0, a point x is equal to x naught is a regular singular point if p of x and q of x are not analytic at x is equal to x naught, but x minus x naught into p of x and x minus x naught whole square into q of x are analytic at x is equal to x naught square. That means we have some freedom. That means we have some freedom for function p of x and q of x. P of x can have a simple pole while q of x can have a pole of order 2. Then such points are called regular singular point. It is to say that it is almost regular. Once again, for simplicity, we assume that x naught is equal to x without loss of any generality. Otherwise, we can shift the origin to x naught. In this case, we can write the coefficient p of x as a 1 by x into some n going from 0 to infinity, p of n into x power n, or explicitly as a 1 by x into p0 plus p1 into x, p2 into x square, and so on. So this to say that it has a simple pole at f of x is equal to 0. Again, note that if p of 0 is 0, then the function p of x is analytic at x is equal to 0. Again, we can expand q of x as a 1 by x square because we are allowed to have x into x minus x naught square into q of x to be analytic. So we express q of x as a 1 over x square plus some n going from 0 to infinity q of n xn, or explicitly we can write it as a 1 by x square into q naught plus q1 into x, q2 into x square, and so on. Now here we notice that if q1 is equal to 0 and q0 is 0, then p of x is analytic at a point x is equal to 0. In this case, we assume the solution of the form y is equal to x to the power s, some n going to infinity, a n x to the power n. That is x to the power s into a naught plus a1 into x, a2 into x square, and so on. This is because now we have some singular point in the coefficient p of x and q of x. We should allow such a freedom for the solution y also. We note that when x is equal to greater than or equal to 0, solution y of x itself is analytical at x is equal to x naught. But if you have a power s is negative or less than 0, then we have some poles at x is equal to 0. So when poles are there, when power is negative, then such solution cannot be considered at x is equal to 0, but in some neighborhood away from x is equal to 0, we can use that. We have seen that this is similar to Lorentz series in the complex analysis. Now we have to determine this coefficients ai's and the power s from ordinary differential equation given to us in the above form. Let us follow the step involved in solving this differential equation. D square y by dx square plus p of x dy by dx plus q into y is equal to 0. So in this case, we have looking at the solution at the regular singular point, and we assume that point is at x is equal to 0. In this case, p of x can be expanded in terms of power series as a p of x is equal to 1 by x, some n going to 0 to infinity pn x to the power n, or explicitly as a 1 by x into p0 plus p1x plus p2x square, and so on. And q of x will have a pole of second order, can be expanded in terms of series 1 by x square into some n going from 0 to infinity qn x to the power n, or explicitly as a 1 over x square q1 plus q1x plus q2x square, and so on. In this case, we are assuming the solution of the form y of x is equal to x to the power s, some n going from 0 to infinity a of xn, explicit x to the power s into a naught plus a1 into x plus a2 x square, and so on. This we substitute in this differential equation and try to find out the s and coefficient a0, a1, a2, etc. We have to differentiate this twice in order to substitute in this equation, and that is fairly straightforward. First differential is given as s a naught into x to the power s minus 1 plus s plus 1 a1 x to the power s plus s plus 2 a2 into x to the power s plus 1, and so on. Now, second derivative can be obtained by differentiating this once again, and we obtain y double prime is equal to s into s minus 1 a naught x to the power s minus 2 plus s plus 1 s into a1 into x to the power s minus 1 plus s plus 2 into s plus 1 a2 x to the power s. This we have to substitute. This we have to substitute in this equation and collect the terms of the power x to the power n and set them to 0 so that the differential equation is satisfied. Let's collect all terms together. The first term is a y double prime, which is we have already written in the previous slide, that is a x double prime, and then we got to add p of x, which is also expanded, but we have 1 by x here, and then we multiply by this with the y prime is the first derivative of the power series solution, which is given also in the previous slide. We add a q, which has a second order pole at x is equal to 0 and expanded in terms of power series, and then finally form of the solution y of x, which we have assumed to be power series, and that we set to 0. Here we have to collect the terms of x to the power n and then set them to 0 for each value of n, so that this equation is satisfied. Now let's collect the lowest power n is equal to 0, or x to the power s minus 2. Now, this gives rise to what is called the initial equation. From this equation, we can determine the value of s, which comes as a x to the power s multiplied to the power series. So, we see that the coefficient of x to the power s minus 2 given as a s into s minus 1 into a0 plus s into p0 a0 plus q0 into a0 equal to 0. Now we see that this has a solution, either a is equal to 0 or s into s minus 1 plus s into p0 plus q0 is equal to 0. So it is straightforward to see that either we have a is equal to 0, in such case the entire series becomes 0. Otherwise, we have when a0 is not equal to 0, we have obtaining a solution for s in terms of p0 and q0, the expansion of coefficient P and Q. So this is how we can obtain the S value. So you see that it is a quadratic equation. We have a two solution for S, which usually gives the two linearly independent solution in the form of power series. The equation which is giving rise to the solution to S0, or the lowest order solution, is called the initial solution, and we can use this to determine the value of S for the power series solution in terms of the coefficient P0 and Q0. Let's go ahead and find out the coefficient higher order powers of x to the power s minus 1 is a immediate order. So we have to collect the coefficients of x to the power s minus 1. This looks somewhat non-trivial with involved calculation, but one has to do it a little bit more carefully. Let us go over this in detail. The first term, which here I have written, is coming s into s plus 1 into a0. That is coming from the first coefficient of x to the power s minus 1. That is s plus 1 into sa1 is what we are getting. The second term, which comes from the multiplication of p1 into x with the sa0 x to the power s minus 1, that would give us the term s into p1 into a0. The next term which we are getting is a multiplication of p0 into s plus 1 a1 x to the power s, that we get the coefficient p0 into s plus 1 into a1. Now the two more terms of the x to the power s minus 1 comes from this term. The first one comes from the multiplying q0 with respect to a1x, and the second term comes with the q1x with respect to a0, and that together give q0 a1 plus q1 into a0 equal to 0. So this is the expression finally we are getting as a coefficients of x to the power s minus 1, which we set to 0. Now we can see that in this case we have the relation connecting a0 and a1 in terms of known coefficient q0, q1 and p0 and p1. This we can invert to determine the relation between a0 and a1. That is, a1 as a minus sp1 plus q1 into a0 divided by s into s plus 1 plus p0 s plus 1 plus q0. Once you are given the initial value a0, we can determine the a1. That is why this is called the recurrence relation. For given s and a0, we can determine the a1, and s can be determined based on the initial equation, and a would remain as an arbitrary parameter which we can set to value 1 without loss of generality. Once we determine the value of a0, we can now obtain the value of an. And then we can solve this for a higher order, that is, next order is x to the power s, and then we would relate a2 to a1 in a similar relation, and that is why it is called the recurrence relation. We can determine all the coefficient a0, a1, a2, etc. based on this relation once we have been given the value of s and a0, and we obtain the solution for the function y of x. So let's look at an example. So we solve an ODE of the form x into x plus 1 y double prime plus 2 minus x square y prime plus 2 plus x into y is equal to 0 using the power series solution. In this case, we have a p of x as a 2x square divided by x into x plus 1. And q of x is given as a 2 plus x divided by x into x plus 1. This we have to expand in terms of power series, which can be easily done using the binomial expansion. We can write p of x as a 2 minus x square divided by x into x plus 1, that is equal to 2 by x minus 2 plus x minus x square, and so on. Immediately, we get the value of P0 is equal to 2. Again, we look at the function q of x, which is 2 plus x divided by x into x plus 1, which can be expanded in terms of binomial series as a 2 by x minus 1 plus x minus x squared plus x and so on. And we get the value of P0 to be 0. And we can solve for an initial equation. In principle, one has to substitute, but we have earlier done for the trial. So we get initial equation as s into s minus 1 plus 2s is equal to 0, or s squared plus s is equal to 0. It is straight away we get two solution, s is equal to 0 and s is equal to minus 1 are the solution for the x to the power s, and that is what we have multiplying our power series. We see that series corresponding to s is equal to 0 has no problem. It is a well behaved at x is equal to 0. On the other hand, the second series corresponding to s is equal to minus 1, which has 1 by x built into the series and would blow up at x is equal to 0. Now it is an isolated singularity, so it blows up only x is equal to 0. If we remove a small neighborhood around that point, we can use this solution. When we want to study the solutions of this differential equation in the neighborhood of x is equal to 0, we can use the solution corresponding to s is equal to 0 and ignore. As I already told, in the case of power series solution, at least one of the solution is going to be well behaved at the regular singularity. We cannot say anything about the second solution. May blow up or it might not. Here is what we have exact statement for a ODE of the form d square y by dx square plus p of x dy by dx plus q of y is equal to 0 with the regular point at x is equal to 0. We have a solution of the form y is equal to x to the power s into some n going from 0 to infinity, a to the power n, x to the power n, that is equal to x to the power s into a0 plus a1 into x plus a2 into x square, and so on. In this case, at least one of the solution is well behaved, that is s would be greater than or equal to 0 at x is equal to 0, while the second solution need not have this property. That means s can be less than 0. Let us stop here and continue with the next lecture.